Hello everyone, welcome to this lecture. So, in this lecture we will see the instantiation for the second component of our framework for the pre-processing phase protocol, namely the perfectly secure triple extraction protocol. So, what are the required properties? We are in the setting where t is less than n over 3. So, we take the case where n is equal to 3t plus 1, that is the smallest value of n satisfying the condition t less than n over 3, and the input scenario for this protocol will be the following. It will be guaranteed that each party has verifiably shared a multiplication triplet through an instance of triple sharing protocol. Okay. So, recall that in the last lecture we had seen that if there is a dealer, then by running an instance of triple sharing protocol, at the end of the triple sharing protocol, it will be guaranteed that there is a multiplication triplet which is secret shared on the behalf of the dealer, such that if the dealer is honest and no one knows the value of the triplet, it is random, except that adversary will have at most t shares for those triplets which are randomly distributed. Whereas, even if the dealer is corrupt for the triple sharing instance, it will be guaranteed that it has secret shared a multiplication triplet, namely whatever is the output of the protocol, it will be a secret shared multiplication triplet. So, the way this triple extraction protocol will be executed will be the following. It will be guaranteed that every party has secret shared a verifiable, it has verifiably secret shared a multiplication triplet, and among these n parties there could be up to t corrupt parties who may not have shared random triplets. That means, those triplets are known to the adversary, but the remaining parties are honest, and there are at least n minus t honest parties in the system whose triplets will be random for the adversary, which comes from the privacy property of the triple sharing. However, the exact identity of the honest parties will not be known. We do not know whether the first party is honest or corrupt. We know it has secret shared a multiplication triplet, fine, but whether the value of that multiplication triplet is known to the adversary or not, we do not know, depends upon whether the first party is honest or corrupt, and no one knows the exact identity of the corrupt parties. Now, we want to run a triple extraction protocol here, which takes a bunch of random and non-random secret share multiplication triplets and output at least which output at least exactly k number of secret shared multiplication triplets, where the value of k is 3t over 2 plus 1 minus t, such that all this output secret shared triplets are multiplication triplets, plus they are guaranteed to be random for the adversary. That means, adversary is guaranteed to not know the value of those triplets. It will have only t shares for each of these k output triplets which are randomly distributed. That is what we want from the triple extraction protocol, and this triple extraction protocol basically involves just one instance of the triple transformation protocol, that is all. So, notice that here all the input triplets are guaranteed to be multiplication triplets, because these triplets are shared by individual dealers using an instance of triple sharing protocol. And we are in the case where n is equal to 3t plus 1. So, if I set n is equal to 3t plus 1 and treat it as 2d plus 1, then the value of d turns out to be 3t over 2. So, I run the triple transformation protocol by setting d equal to 3t over 2. Because of the triple transformation protocol, now there will be a very nice correlation among the transformed secret shared triplets. The correlation will be that there will be polynomials of degree 3t over 2, 3t over 2 and 3t, namely a polynomials, b polynomial and c polynomial, such that the a component of all the transformed triplets lie on the a polynomial, the b components of all the transformed triplets lie on the b polynomial, and the c component of all the transformed triplets lie on the c polynomial. Also, it will be guaranteed that at most t points on the a, b and c polynomials are learnt during the triple transformation protocol, because the triple transformation protocol has the privacy property which guarantees that the ith transformed triplet, will be random for the adversary if the ith input triplet was random for the adversary. That is the privacy property of triple transformation, right. For that you can refer to our earlier lecture. So, that means if say the first party was honest, the first party P1 was honest, then during its instance of triple sharing, whatever triplet is at secret shared at the end of the first instance of triple sharing, that will be random for the adversary, and as a result of that the first transform triplet will be random for the adversary. Whereas, suppose the ith dealer was corrupt, but it has secret shared some triplet, as a result of that the ith transform triplet will be known to the adversary. The same way, suppose the nth dealer was honest, that means the value of the multiplication triplet shared by the nth party is random for the adversary, then the nth transform triplet will also be random for the adversary. So, and since this transform triplets constitute points on the a, b and c polynomials, it means that adversary will be knowing at most t points on these triplets corresponding to the t corrupt dealers in the system. Okay. Now, we also know that since each of these input triplets are multiplication triplets, it is guaranteed that the C polynomial is equal to the product of A polynomial into B polynomial. Okay. So, what we do here is the following. Our goal is to get k number of output triplets. Those k triplets are obtained by defining k new points on the A polynomial, B polynomial and C polynomial. So, we define the A polynomial at beta 1 to beta k, B polynomial evaluated at beta 1 to beta k and C polynomial evaluated at beta 1 to beta k. So, we already have the points alpha 1 to alpha n which are used while defining the A, B and C polynomials. Apart from that, we also require additional k number of beta points here which are different from the alpha points, and this puts an additional restriction on the field. Now, we require the field to be at least n plus k. Okay. Now, these new points on the A, B and C polynomials can be computed as a linear function on the old points on A, B and C polynomials. By old points I mean the transform triplets. Notice that the transform triplets are not available in clear to any specific party, they are secret shared. So, since the new points on the A, B and C polynomials can be computed as a linear function of the old points on the A, B and C polynomial, from the linearity property of the secret sharing, it follows that given the secret sharing of this transform triplets, the parties can locally and non-interactively compute a secret sharing of this new points on the A, B and C polynomials, and this is taken as the output for the protocol. Okay. So, we now want to claim that this k secret shared triplets are multiplication triplets and they are unknown to the adversary. So, first of all, why they are multiplication triplets? Because they lie on the polynomials A, B and C, and we know in this case the C polynomial is equal to the product of A and B polynomial, because irrespective of whether the dealer of a triple transfer, whether the dealer for the triple sharing instance is honest or corrupt, all the triplets shared by the individual dealers are guaranteed to be multiplication triplets. That means, at the end of the first instance of triple sharing, the triplet A1, B1, C1 is a multiplication triplet. At the end of the ith instance of the triple sharing, the triplet AI, BI, CI is a multiplication triplet, and at the end of the nth instance of the triple sharing, the triplet AN, BN, CN is a multiplication triplet. That means, all the inputs for the triple transformation is a bunch of secret shared multiplication triplets. As a result of that, the output for the triple transformation is a bunch of secret shared multiplication triplets, and since transform triplets lie on A, B and C polynomial, the C polynomial is the product of A and B polynomials. And the output triplets of this protocol are also lying on the A, B and C polynomials. That automatically implies that all these output triplets are multiplication triplets. Why they are random for the adversary? Well, at the end of the triple transformation, among these transformed triplets, adversary will be knowing at most k of them. Okay, we already argued that. And what exactly is the degree of A polynomial? The degree of A polynomial is 3t over 2. Okay. So, the degree is 3t over 2, that means we need 3t over 2 plus 1 number of points to uniquely identify the A polynomial. Among them, adversary will have only knowledge about t points, okay, corresponding to the t transform triplets. That means, how many points are unknown for the adversary? It is k, which is 3t over 2 plus 1 minus t. These many points in the A polynomial are unknown for the adversary, and they could be any unknown points, because they correspond to the A components of the triplets shared by the honest dealer, which at the end after transformation also remain random for the adversary. Now, whatever value those k number of unknown A components can take, that determine the A components of this k output triplets. That means, there is a 1-to-1 mapping, there is an injective mapping, there is an injective mapping between the unknown A components here in the A polynomial, which are not known to the adversary, and these output A components. And since the unknown components are random, they are randomly distributed. Of course, adversary will have t shares for each of them, but they are randomly distributed. That does not help the adversary to find out the exact values of those unknown components. That automatically implies that even this k number of output A values are random for the adversary, except that adversary has t shares for each of them. The same argument holds for the B polynomial. Even for the B polynomial, its degree is 3t over 2 plus 1. Adversary will be knowing at most t points on this B polynomial. The remaining k points corresponding to the honest dealer are unknown on this B polynomial. For the adversary, they could be any random point, and as a result of that, the B component of this output triplets will be random for the adversary, and same argument holds for C. Since A and B polynomials are, since there are k number of points on the A and B polynomials which are random for the adversary, that automatically implies that even the corresponding k points on the C polynomial are random for the adversary, and as a result of this, the k number of C components here which are obtained as the output will be random for the adversary. So, that proves the privacy property of the triple extraction protocol, and you can see that it is a perfectly secure protocol because all the properties here are achieved in an error free fashion against a computationally unbounded adversary. And now we have the instantiation for the triple sharing gadget as well as the triple extraction gadget. and in one of our earlier lectures we had seen that if you have the triple sharing protocol and if you have the triple extraction protocol, then by combining them, by stitching them, you can obtain a pre-processing phase protocol. That part we had already discussed in one of our earlier lectures. Okay. That means now you have a perfectly secure protocol for the pre-processing phase by running which the parties can generate secret sharing of CM number of random multiplication triplets, where CM is the number of multiplication gates in the circuit. That completes our discussion on perfectly secure MPC. Now we have a perfectly secure MPC with T less than n over 3 tolerating Byzantine adversaries. And we had already argued that T less than n over 3 is the necessary condition for any generic perfectly secure MPC, because there are some specific tasks such as perfectly secure Byzantine agreement where the condition T less than n over 3 is necessary. That shows that the condition T less than n over 3 is necessary for any generic perfectly secure MPC computation protocol. Thank you.